Okay. Wow, you're quiet. Are you tired? Was lab tiring for some of you? Monday, I'm not getting any response. What's that?
So Wednesday is so much more efficient than Monday.
Oh, not so much. In some ways, but not so much. Also, Monday is lucky for Thanksgiving. You don't have to be here on Monday. Those of you that I was trying to get them to move to Monday. Oh, is this for somebody here?
That's been there for a week.
Huh?
That's been there since then.
It's been there for a week? Oh, good. Okay. Let's pick up where we left off. So let's try to refresh your memory. Who remembers when is the quiz? Monday the 18th?
Yeah.
Okay. At least you don't have a rabbit hole to do that. Okay. Good. I'll have to see where I will let you know what material goes in the quiz, depending on what we finish. Okay. So, name examples of adsorption chromatography. Mode of separation that are considered adsorption chromatography. Are you Anya?
That's Anya. I'm Sally.
Sally, I think you are. Okay.
That's an ion exchange.
Ion exchange is correct. Yes, is one form of adsorption chromatography, and actually within ion exchange can be cation or anion. What else can be considered adsorption chromatography? I know you know, but go ahead. I'm just seeing somebody else. Affinity chromatography is also adsorption. Is another one. See?
And it's partition.
A partition chromatography is a different category. Partition chromatography is when you have two liquids, they partition between the two, stationary and mobile phase are liquid. Adsorption is when the stationary phase is solid. What other than ion exchange and affinity? Yes, Eddie? Hydrophobic interaction. Yep. What molecular interactions between solute and stationary phase are involved in size exclusion? What kind of interaction? None. So size exclusion is physical separation. So it's based on size. So that's why it's called size exclusion, gel permeation. So that means the same thing. Okay, separation is physical. What about ion exchange? Michael?
All of them?
An ion exchange?
Isn't it hydrostatic, electrostatic, hydrodynamic? Oh, wait, it's just.
There's no
electrostatic.
covalent bonding in any.
Okay.
And then an ion exchange is the interaction is by charge, so electrostatic charge. HIC. Hydrophobic interaction chromatography. So the interactions, yes, hydrophobic, yes. And what about affinity, Michael?
All of them.
Yes. I want you to get that right, all of them. Yes. Okay. What's the difference between cation and anion exchange? Yeah. What is anion exchange? What is cation exchange? Stationary phase for the cation exchange is negatively charged, so we can exchange cations, interact positive charge with negative charge, and then the anion exchange is the opposite. So the function will be positively charged, and anions are being used. Now, this is a very common question I would ask. How do you increase the strength of the mobile? And it's different in different cases. So how do you increase the strength of the mobile phase in reverse phase chromatography? Add non-polar. In reverse phase chromatography, your stationary phase is non-polar, the mobile phase polar. To increase the strength so that the solutes come out of the mobile phase, you make it more non-polar. What about, it's not here, what about normal phase? How do you increase the strength in normal phase? Yes, Elizabeth? Add more water. Because in normal phase, we start with a polar stationary phase and an organic non-polar solvent. So we increase the strength by adding water, increasing the concentration of water. All right, how do we increase the concentration, the strength of the mobile phase in hydrophobic interaction? So do you remember what your mobile phase would be in hydrophobic interaction to start with? Do you remember? Phase?
Usually it's like 1 mole or a mole sulfate.
So it's high salt concentration. So if it's high salt concentration, your proteins charges are covered by the salt, so they interact better with your hydrophobic stationary phase. So now if I want to get them out, I want to increase the strength of the mobile phase. What do I do with the mobile phase? What do I do with the mobile phase? I know you guys know, I need the others that are shy. So you start with salt, you want the protein to come out. What do? And
What do you like start decreasing the concentration of the
absolutely, you start decreasing the concentration of salt down to 0, where it would be only water. Okay, so good. In ion exchange, this is tricky. So in ion exchange, what you do is you would run in your sample at a specific buffer with a specific buffer at specific pH and salt concentration. If I have, let me give you this. It is very tricky and confusing at times. So if I have, let's say, an anion exchange. So I have positive charges on my column, my stationary phase. And I have a negatively charged, some carry multiple. Okay. Negative charge, and I'm running, let's say at pH 6.5. So at pH 6.5, my ions are, in this particular case, are negatively charged. And they're interacting with the column. Now I want to elute them. I want them to reduce their interaction with the column. What do I do to my pH? Do I increase the pH? Do I decrease the pH? What do you think would be best?
I think you increase the pH, correct?
So tell me what happens if you increase the pH. What happens?
So my thought process is we want to make the column more negative so that they don't interact. And I was thinking that increasing the pH would make your column more negative.
Okay, so you have somewhat of a right approach. So if I increase the pH, I have more OH minuses. So they're going to compete with these ions and interact with the column, positive charge, blocking the positive charge. So these won't interact. So this might work. But sometimes if you have a really high valent ions with a lot of negative charge, the OH minus is not going to compete as well. It might work, it might elute, but sometimes you'd say, oh, this is difficult, it's not working very well for me. So what you can do, so in one case, you can do that, but in some cases, when you have really strong ions here, what you can do is reduce the pH. If you bring the pH down, let's say to 3, these are going to be protonated. So they no longer carry negative charge, so they will not interact with the ion. So it can go both ways. In the book, in the table, it tells you decrease the pH. Increase the pH is not wrong, but you want to justify what you mean by increasing the pH, what happens. Another way is increasing salt concentration, ion strength. So the salt now, the negative charges of the salt will compete for interacting with the column, and then they can elute. So it is somewhat challenging depending on the compounds that you are separating and the buffer you're using. Sometimes if it's protein, you want to be careful not to get to a pH close to the isoelectric point. Then protein will precipitate on the column. You don't want that to happen. So it really depends on your molecules, and you have to have a good understanding of your molecules, and then you have to try things out and see what works. But changing the concentration of salt, changing the pH is what you would do to increase the strength of the mobile. In which direction? It depends. Whatever you choose, you have to explain it carefully, and you would get a check mark on it. Even if I want you to say decrease and you said increase, if you explain it correctly, then I'm fine with it. As long as you explain what happens when you increase the pH and what happens when you decrease the pH. How do you increase the strength in affinity chromatography? There are two ways. There is specific and non-specific. Do you remember any? Just to remind you, affinity chromatography, you have to have specific interactions. So there should be specific pH, temperatures, ion strength for the interaction to happen. So how would I change or increase the strength? Okay, we're having not so great of a Monday, some of you. You're tired, I'm tired too, so it's okay. So you change the mobile phase two ways. If it's specific, you can add ligands. So if you remember, so you have your support, you have a spacer, and you have some form of a compound attached to it. And then your compound of interest, let's say antibodies, are going to very specifically bind to this ligand. You can increase the ligand concentration in your mobile phase. So you have more ligands, so this is going to start binding with that in the mobile phase and elute. Okay. What is the order of solution in hydrophobic interaction chromatography? So what elutes first? If I'm separating proteins, which is the most common use for hydrophobic interaction chromatography, the most hydrophobic will come out first, or the least hydrophobic will come out first? Yes, Ellie. You're there. Oh my gosh, Ellie is sitting next to you. So Sally and Anya and Ellie and Sarah, I'm going to confuse you. Okay. The least hydrophobic will elute first, absolutely. The more hydrophobic the protein is, the more it's going to interact with the column and stay on the column, unless you add something. Sometimes even in hydrophobic interaction chromatography, water is not enough. So we add NaOH, which is alkaline, to get the protein out. To increase the charge on the protein to let it come out. In ion exchange, what would be the order of elution? In either case, whether it's positive or negative. So the least ionized or the most ionized will come out first. The one that carries the least amount of charge or the one that carries the most amount of charge? Michael?
The least.
The least, okay. So the more ions, the more charge the molecule carries, the more valence the molecule have, the more interaction it will have with the top. In size exclusion, what's the order? Okay, no. Size, the larger comes out first. So the larger molecules will not have access to the pores, to the different pores. They won't go through the pores. They will travel within or between the pores, between the particles. So the larger ones will come up first, and the smallest will be detained due to going into all the pore sizes in the particles of your column. Okay, we have questions. How do we increase the strength of non-specific by changing the pH or ion strength? So this will impact the charges on the molecules, so they will not interact.
And then there's a lot of this information summarized in that table you have on the slide.
Yes, yes, definitely. So that table is very important for you to study. Okay. So moving into the last topic of principle of chromatography, which is resolution. That means developing a separation. How do we develop a separation? This comes with experience and a lot of trials that you would want to do. But the idea here is before you do anything, what's the simplest way of going into the lab and running a chromatography? Before you do that, what's the simplest way in knowing what to do? Abi?
Check for the flag.
Huh?
The flag.
Before you do that, before you indulge, Saj, what were you going to say? Were you? Did you have your hand up? Why not? Okay, so, yeah, what do you do? Sam?
We're just maybe knowing what you're saying.
Before, you said, I don't know anything. Michael?
We usually just Google it.
Instead of Googling, do scientific literature search.
Sure.
Yes.
Tolerant.
No, well, you can Google, but you would look up literature to see who did carotenoids before me or who did caffeine. Somebody, I bet you somebody had done that before. So the first thing you want to do is see what's published. That's the easiest. And from what's published, you go in and start the method. Is it going to work? 99.9% is not going to work. It's just you have to modify. Sometimes it works, but not so well. You have to go in and make modification based on the color you have, based on the system you have. So you have to make some modification. And in order to make modification, is you need to know your sample. Yes, you want to know if it's polar, if it's non-polar, is it charged, what's the molecular weight? What do I know about this? Does it like hydrophobic columns? Will it interact more with hydrophobic columns? What do I know about the components within the samples? Do they absorb light? Do they fluoresce? Do they not absorb light or fluoresce at all? What do I use for them as a detection method? And then how many components need to be resolved or separated? Is it 2? Is it 10? Is it 20? Sometimes the number can be large, too many. And then what degree of resolution I need? Do I need them to be very well separated so that I can get the area of each and be able to quantitate? Or I don't care, I just want them to separate, I just want to determine identity. Are they there or are they not? And what are they? If I'm not quantitating, like this separation is really hard to get an area under the curve. You go this, you would just say in the middle, but it's not really true because the peak is right there and the peak ends here, so you cannot get peak area separate from each. So this is really poor resolution if you want to quantitate. If you want to identify, actually this is fair enough. So you would determine what works for you, and then you work hard to get, if you need separation, you work hard to get that separation. Qualitative, quantitative, that determines how much separation you want to get. All right, once you know your compound and you know how many compounds are there in the sample, then you want to choose chromatographic separation mode. There are plenty to choose from. So sometimes you can do reverse phase as well as normal phase, but sometimes reverse phase give you better separation. We'll give examples when we talk about separation of small sugars. Separation of small sugars can be done with normal phase, reverse phase, anion exchange, cation exchange. You can do that with the sugars, except you will modify or pick based on the different components you have and based on your knowledge and capability. Sometimes it's as simple as I have a column for that, that would work. I don't want to purchase an $800 column. So you work with what you have. So there are a lot of options to choose from, but sometimes you have to pick based on availability of what you have. And sometimes if you have two systems, then you pick which one gives me better resolution and separation that I'm looking for. So once you establish what you want to go with, which chromatographic separation, then even you have to choose the stationary phase and mobile phase. So let's say you chose reverse phase chromatography. Okay, in reverse phase, there is C8, C18, C40. So you have different stationary phases, even within one mode of separation, which is a reverse phase chromatography. If you have size exclusion, there are multiple columns you can choose from based on the range of the molecular weight you're separating. So there are a lot of options you have to consider. And then go, okay, if I'm separating caffeine, C18 would work. If I'm separating carotenoids, I need a C40 column. So then you would determine which column to get or which stationary phase to get. And same with mobile phases. Sometimes you use water and methanol. Sometimes you need a stronger organic solvent to use water and acetonitride. So it really varies. So you have to select the stationary phase and mobile phase to go with. Okay, lots of options. Then you want to choose if you want to go isocratic, gradient. You start off with isocratic normally. You go, I just want to see what I'll get if I keep my mobile phase constant. Okay, this is taking 2 hours to get all of my analytes out. That's not going to work. I have 200 samples to inject. Then I start thinking about gradient dilution. It will sharpen my peaks, it might enhance separation, and also I will shorten the analysis time. Then you go with flow rate. We'll talk about flow rate. It has a very important role in resolution. You don't want it to be too slow. If it's too slow, your compound will move down the column by diffusion instead of partitioning. So going down the column by diffusion, you have a very broad peak. So instead of another column, and then your sample is injected as a narrow, it will be a very narrow band, will give you a very sharp peak. But if you have very slow flow rate, you start having diffusion. Your band we're going down the column by diffusion. Then you end up having a broad peak. When you have a broad peak, if you have a peak next to it, it won't be separated. So you'll get this shape. But if you have high flow rate, then you can get two separated here, like that. So you have two sharp peaks separated. So flow rate is really important. But if it's too fast, if your flow rate is too fast, these two peaks will be one peak. That comes sooner, there's no time to equilibrate, there's no time to interact with the column. It's just the mobile phase is really going very fast. I lose separation. So flow rate is important. You have to find that sweet spot of flow rate to get the separation you want, but at the same time, no co-elution. Temperature is another important factor. Temperature is important because as you increase temperature, what happens to the viscosity of your mobile phase? With higher temperature, what happens to viscosity in general? It decreases, right? So mobility is enhanced. So first of all, you have kinetic energy. So with higher temperature, you have faster movement. And also you have lower viscosity of your mobile phase, then the compounds can move faster and equilibrate faster. Then if you increase the temperature from room temperature to 35 or 37, you enhance separation and shorten your analysis time, and you have really nice sharp peaks. Too high of a temperature might corrupt your column. One thing you want to be sure that your temperature is within the range of stability of your column, stability of your compounds. And if it's too high of a temperature, it might also cause a co-elution by going very fast and not having enough time to separate. Okay, so these things, we call them elution mode, whether isocratic or Braggian, the flow rate, and the temperature, which we can control by putting our HPLC column in an oven. Okay. Yes.
Can you say if the heat will reduce, the heat might reduce, but it's already away. So if there is an issue, that one impact, so can you say it's good that?
Yeah, it doesn't matter. It doesn't have to always be a really sharp peak. If your compounds are separated, that's fine. It's fine. It's okay. As long as you get separated.
I think it's actually whether you say compound deteriorates, so you lose compound. So if you lose compound, just quickly what you say.
If the compound degrades, then you don't want that. That's added. You don't want your compounds.
Yeah, I need just the separation.
Yeah, if the separation is fine, it doesn't matter. It doesn't have to be sharp. What you care for is the area under the curve, which correlates whether it's long, sharp, and narrow, or wide and short, gives you the same area if it's the same concentration. Okay. So I want to introduce you now to a few terms that you will hear as I explain resolution and how we can determine resolution of our system. So you will hear retention volume. So basically, this is the volume of the mobile phase we needed to get the compound out. So you can use retention volume or retention time. You can use retention time and flow rate to calculate retention volume. So oftentimes, it's what we look at is retention time, which is the time it took for a compound to leave the column and reach the detector. So that is retention time. What we often do, like we did today in the HPLC lab, is determine the retention time and compare it to a standard. When we run our standard, we ran the standard caffeine, we got a retention time, let's say, of 16 minutes. And then we ran Pepsi and we found the caffeine coming out at 16 minutes. So we said, okay, that most likely is caffeine. That's part of the story, but that's an example, is comparing it to a standard. If two compounds are coming together, no matter what you do, no matter how you change your mobile phase or flow rate or what have you, you're not getting good separation. You do a second separation. So we call it 2D chromatography. That means we separate, let's say, by size exclusion, and then we separate by ion exchange. So we can enhance separation of compounds by utilizing different modes of separation. So some compounds have the same size, but different charge. Some compounds have the same charge, but different size. So if you use one or the other, you won't get separation. Adjusted retention time. So some of you in lab today saw the solvent front, which is a peak that from the time of injection till the time of the solvent reaching the detector detects something. So it gives you a detection. And this would be your solvent front or the void from time of injection to time of reaching the detector. So this is different between different systems. It's really dependent on the system, the tubing, the lens you have. So the column specifics that you have. So it really depends and varies. To account for that, you get T prime retention time, which is basically adjusted retention time. That means the retention time of the substrate or the compound of interest minus the retention time of the solvent. So you get the adjusted retention. Okay. And then there is a separation factor. The separation factor, alpha, is adjusted retention time of peak 2 over adjusted retention time of peak 1. The greater the alpha, the greater is the separation. So this gives me the power of separation. So this, as I mentioned, the separation is affected by temperature, not only stationary and mobile phase, but also the rate, the flow rate. Okay, any questions? Because I'm going to move into a little bit more complicated. Okay. If you have a question, you can ask me. Okay, we'll wait. Then we have a side tutoring happening. What?
Go back.
Go back? All right, well.
Yeah.
T, retention time T. This is, are you asking about this?
Yeah.
So this is the time it takes between when you inject the sample, to the time from injection, the mobile phase reaching the detector. That's the solvent time. From time of injection, it moves. Okay, so the mobile phase moves from 0 time to where it reaches the detector. The detector detects something here. It gives you a signal. That's the solvent time.
So if we need the first peak, which time we can take for the first
This one?
Yeah. So
There is a retention time that you take from injection to here, or you can take the adjusted retention time.
for me, it's the adjusted retention time and the detect time are not the same. That's why.
Not the same. The retention time, if you're using the same HPLC, the same column, and then you're comparing data of standard to sample, you don't care about this because you're using the same system. If you want to look at the reference that use a different instrument but the same compound, you account for the solvent front, then you can compare that with the retention. Okay. Alright, so resolution of two peaks from each other is referenced here as resolution, RS. So what you see here is 2 delta T, that means the difference here. So this is peak 1, peak 2. Delta T is the difference between the time difference between two peaks. You take into account the width of peak 1 and the width of peak 2. So the wider the peak is, the poorer the resolution is going to be. Okay? The wider, whatever parameters you have, the wider the resultant peak, the lower is your resolution. And the more separation you get, that means the bigger the difference between retention time 1 and retention time 2, the better the resolution is. Okay. So this is just putting things in perspective in respect to what resolution means. Separation between two peaks, it's impacted by the width of the peak, and it's impacted by the retention time. Okay. All right, so this is the simple format of resolution. This is the equation that takes into account different factors. So resolution is impacted by the theoretical plates. And this is efficiency of the column, A, efficiency of the column. B is selectivity of the column. That's second factor. C is the capacity of the column. So resolution is dependent on the efficiency of the column, the selectivity, as well as the capacity. So 3 different factors impact resolution. Now I'm going to talk about each factor to explain each factor. All right, so the efficiency of the column is related to the theoretical plates. Okay, what is theoretical plates? So theoretical plates, basically they're theoretical. So the column is not really divided into any segments, but each segment for a theoretical plate in the column designate equilibrium. So as the compounds, etc., as the compound go into the column and they are separating between the column and the mobile phase, they reach equilibrium. The time it takes or the distance it takes to reach that equilibrium is called the theoretical plate. So the more theoretical plates you have, the sharper is your peak. And the smaller the length of the theoretical plate, or the shorter it is, the narrower is the peak. When the column deteriorates, that means you have the not good separation and it takes a long time to reach equilibrium. What happens is the number of theoretical plates decreases. Then you have longer distance to reach equilibrium. When this happens, then this is your peak. The peaks widen instead of being sharp, with the bands going down and remaining sharp band, versus dispersing within the column and becoming wider peak. So this happens with more use of the column. So with extended use of the column, you lose selectivity, you lose capacity. So then you have much longer time to equilibrate. And actually, each compound has a unique theoretical plate because each compound is unique. It takes different time for equilibration. So in order to determine what happens to the efficiency of your column over time, you start with a compound, whatever that compound is, and you measure, you inject the same compound every 3 months, 6 months, or a year to see if the calculation of the theoretical number of theoretical plate changes. So this is basically what it is. You calculate it based on the width and retention time. And then you see if your number of theoretical plates changes over time, but you have to use the same compound because every compound will have a different calculation. So the number of theoretical plates is proportional to the length of the column. The longer the column, the more equilibriums you get, the more number of plates you have. Okay, but the more important than the number of theoretical plates is the height equivalent of a theoretical plate. This is more important, the height of each theoretical plate, which is the length of the column divided by the number. It gives you the height equivalent of a theoretical plate. The narrower the height, the better the separation, the better the resolution. So this is basically showing you the Van Demeter equation. Height equivalent of theoretical plate is also dependent on 3 things. Eddy's diffusion. Let's explain Eddy's diffusion. Okay. So Eddy's diffusion. What is Eddy's diffusion? You have a column that is packed with large molecular particle size material, and then you have a column packed with small molecular size, or not molecular size, particle size, sorry, material. Think of a pebble, small pebble and large rock, and you have a river. The river is your mobile phase. So if you have a large rock, what happens is you have different paths that your mobile phase can take. So your molecule, your compound will diffuse into the sample, into the column, into the stationary phase more. And will the peak, the band would be large, will give you a wide peak. If you have small particle size of your packing material, so you don't have very many paths, and it goes down and equilibrates faster. So you have really sharp bands, which translate into sharp peaks down the column. So that's Eddy's diffusion. It has to do with the particle size of your column. Small particle size packed really well with small spaces or vacant spaces, the better is your eddy diffusion. The smaller is your eddy diffusion. It doesn't diffuse more into the column. So the smaller is the A value, the smaller is the height equivalent theoretical plate. Now, the second one is basically longitudinal diffusion. Longitudinal diffusion meaning, so your compound starts with a really sharp band here at the top of the column. And then it just starts going in and out, but at the same time, it's going down the column by diffusion. It's not only going down because the mobile phase is going down when it's in the mobile phase. It's going down like this through diffusion, and it's also going down through going in and out and going through the column. So this is impacted by the flow rate. So if the flow rate is too small, you're going to get more of Eddy's diffusion, longitudinal diffusion. So you get wider band. If the flow rate is high, this factor doesn't really contribute much to the high equilibrium effect. So that's where the flow rate plays the role. Last factor is mass transfer, which is going in and out. This is impacted by the thickness of the stationary phase. If you have a wide column versus a narrow column, if you have a packed column versus a capillary column. So what does that mean? This is important for when Gary starts talking about capillary columns in GC. If you have very thin material here, and your sample is going through here, it doesn't have much of a diffusion in there, very narrow, very thin. It will equilibrate really fast because you don't have that much material. Also, if you have a narrow column, you also don't have very much material for the samples to go in and get lost and detained. So this mass transfer is impacted by the thickness of your stationary phase, how narrow or wide the column is, and also is a factor of the flow rate as well. If you have too fast of a flow rate, then you also won't get separation, you'll get dilution. So flow rate is really important. You want to find this equation kind of demonstrate that the flow rate shouldn't be too slow and shouldn't be too fast, because too fast of the flow rate will impact mass transfer and you don't get the equilibrium. The compounds will come out without equilibrating and they won't get separated. Are you overloaded? I'm sorry, but this is important, basics that we need to cover in order to understand chromatographic separation.
So the HETP is basically the overall, like that's how we measure efficiency.
Yes, exactly. And it has to do with the height of a theoretical plate. So the smaller the height, the shorter the height, the better the efficiency of the column, the narrower is your band. Yeah. Okay, so I'll stop here. I'll see, I still have, I think, a few slides to go over. Maybe 6, 7 slides. I'll see if I can take 10, 15 minutes from there and on Wednesday to finish this the resolution of the piece. Okay, thank you.